Hello everyone, welcome to this video. In this video, we shall see certain properties of Fourier transform. In the last video, we studied about Fourier transform, how it works, how we can calculate the inverse Fourier transform. So you are already familiar with these formulas. So when you wanted to calculate the Fourier transform of some function f of t, it would simply be the integration from minus infinity to infinity that function f of t e to the power minus iota omega t dt, and we can call the whole of this quantity as capital F of omega. Now capital F, that represents the Fourier transform of the function f of t in the omega domain. So that means you have shifted your function from this t domain to the omega domain. And similarly, when you shift your function from the omega domain to the t domain, it would simply be obtained using this relation of inverse Fourier transform, that is 1 by 2 pi integration from minus infinity to infinity f of omega e to the power minus iota omega t b omega, which is given to be f of t. So let me give you in brief all the properties of Fourier transform so that you could have a better understanding. We'll study all of these properties later on in the course. So the first property here, before moving on to the properties, I'm defining some general notion here which is applicable to every property, right? It says that if f of t, that is piecewise continuous, if f of t is piecewise continuous, we are assuming in every property the function f of t is piecewise continuous, it is absolutely convergent, and moreover when you take the Fourier transform of this function, it is nothing but capital F of omega. So that is how we are defining the properties. So the first property over here, it says that we are talking about linearity property. Now this property tell you that when you take the Fourier transform of any linear combination of two functions, so it would be the linear combination of the Fourier transforms of those functions. So all in all, you can clearly see that this f, this is a linear operator. The Fourier transform, this is a linear operator. And in a similar manner, you could also write down the property for inverse Fourier transform, right? So it would be applied onto some omega domain. So your function would be like this, d g of omega, right? So you could write this to be c Fourier inverse of the function f of omega plus d Fourier inverse of the function g of omega. So all these properties, they also work in the opposite sense. Moreover, moving on to our next property, we have shifting on t-axis. Now we'll see this in detail. What do you mean by shifting on t-axis? So that means whenever you are shifting the independent variable t by the distance t naught, either in the right direction or in the left direction, depending on the sign of t naught, whether it is positive or negative. So according to that, it would just be available if you have the Fourier transform of the function f of t, which is capital F of omega, multiplied by this term. So this term is additional here. So that means you do not have to calculate the Fourier transform of this function again. You just obtain it by using the Fourier transform of the given function f of t. So this property is quite useful. And this property, shifting on omega axis, is also available. It says that if you wanted to calculate the Fourier transform, or because we are now talking about this omega axis, so it says that whenever we wanted to calculate the Fourier inverse of this shifted version of the given function f of omega, so it would be multiplied by this factor e to the power iota omega naught into f of t, right? Otherwise, if you calculate this Fourier inverse of capital F of omega, it would be nothing but this function f of t, right? So I think you got this understanding that what we are trying to do over here. So you can also write this property in the reverse sense. So that means you could shift this operator here, so you'll have something like this, right? So moving on to the next property, we have scaling property. Now what does it say? It says that whenever within the independent variable you are multiplying this independent variable by some quantity a, so that means you are scaling your function. So that means you are either magnifying it or you are either compressing it. So in that case, the Fourier transform simply becomes that of 1 by a. So you have to divide by a whatever is the result of the so that means you had earlier, you already knew what was the Fourier transform of the function f of t, right? It was capital F of omega. Now you wanted to calculate what is the Fourier transform of f of at. Now instead of using the definition all over again and calculating it over again, what you do, you just replace this omega by a. So you will have f of omega by a here, and you'll divide this whole thing by 1 by a. So that is what this property tell you, and in the other sense it is like this. Next, a particular case of this property, scaling property, it is the reversal property. It tell you that whenever you wanted to calculate the Fourier transform of the function of minus of t, so it would simply be the Fourier transform of minus of omega, right? Okay, so we have next property, which is the modulation theorem. Now what does it say? The modulation theorem, it says that whenever you are modulating, that means whenever you are multiplying either by the cos term or by the sine term, your function would be changed like this. So that means you do not have to calculate this whole thing again. What you do, whatever is the Fourier transform of this function f of t, which was f of omega, you just do manipulations into this function. So what you do, first time you add omega naught here, then you subtract omega naught here, then you add omega naught here, subtract omega naught here, take the sum and divide by 2, take the difference, divide by 2 and multiply by iota. You'll see that in the later videos how do we obtain this particular quantity. Our next property is the symmetry property, which is also known as duality property. So it tell you that, now you can see here the difference. This is capital F of t and this is small f of omega. So our initial function f, that was defined in the t domain, and whenever you applied this operator f onto this function, you obtained capital F of omega. So this duality property gives you a relationship. That means whenever you are trying to have to solve this function in the t domain, so what is the Fourier transform of this particular function in t domain? It would be 2 pi times the this small f function when you have minus omega in place of t. So this is the symmetry property. Next we can also calculate the Fourier transform of derivatives of some functions. So for that we need to define certain conditions. First of all, we'll see what is the differentiation of with respect to t. So the differentiation, suppose we are given f of t function, so its differentiation nth derivative would be defined like this. So what are the conditions that are required here? We are saying f, the kth derivative of f should be piecewise continuous on the given interval, and moreover it should be absolutely convergent. So that means whenever you are defining something like this, you should have all the derivatives up to this nth order as the piecewise continuous and absolutely convergent derivatives. And so if that is true, then we can apply this Fourier transform onto the derivative of this function. So it would be iota omega raised to power n, whatever is the order of derivative that is same as this power into f of omega. Now what is this capital F of omega? This was nothing but the Fourier transform of the function f of t, right? So you can see that whenever you have this nth derivative over here, so we are multiplying omega n times here in addition to iota. And in a similar sense, you can also write this property with respect to whenever you are having differentiation with respect to omega. So whenever you are having differentiation with respect to omega, that means this function is differentiated n times. So this quantity becomes equal to the Fourier transform of the function f of t multiplied by t to the power n. Now you could also see this property in the sense that whenever you multiply some function by t to the power n, what you get here, you get the nth derivative of the given function capital F of omega, right? So this is the another property that we have. So from this differentiation property we got two results which are quite useful. So we can also define this result in the reverse sense. We could also define this result in the reverse sense. So you have Fourier inverse of, so you could shift this operator here, so it would be like this: Fourier inverse of this function is equal to, you could shift this iota to this side, so it would be minus iota raised to power n t to the power n f of t, right? So this is the differentiation property. So we have generalized this property. So what if I wanted to calculate the Fourier transform of the first derivative of the function t? So according to this formula, it would be iota omega raised to power 1 into f of omega. And similarly, if I wanted to calculate the Fourier transform of the second derivative of the function f of t, it would be iota omega raised to power 2 into f of omega. Now iota square is nothing but minus, so we have minus omega square multiplied by f of omega. So this is our result, right? Similarly, you could calculate any order Fourier transform of derivative of any order. The next property we have is that of integration. So when you wanted to calculate the Fourier transform of integral, so in that case you should have the condition on the function that it should be piecewise continuous, it should be absolutely convergent, and moreover f of 0 should be equal to 0. If that is the case, then you can define the Fourier transform of the function as this thing. So Fourier transform of the integration infinity to t f of tau d tau. Now notice here that it is from infinity to t, right? So what is this? It is 1 by iota omega f of omega. So whenever you are taking the Fourier transform of integration, so you are dividing by omega, and when you are taking the Fourier transform of derivative of some function, you are multiplying by iota omega. So this point should be remembered. And this is for the first derivative, for the first integral. If you are having n such integrals, so what would be the change here in this result? It would be iota omega raised to power n into f of omega. Next we have with us the convolution property. Now convolution is very important in electrical engineering applications when you have different signals and you wanted to merge different signals, or you wanted to separate different signals. In those situations you are required to perform this convolution operation. Now this convolution operation, we'll discuss in the later videos what is it, how do you perform that. So in certain cases, whenever you wanted to calculate or perform the convolution, the Fourier transform of convolution of two functions, so instead of using the definition to solve it, we have a very simple and useful property which says that you calculate the Fourier transform of function f individually, function g individually, and then whatever are their Fourier transforms, you just multiply their results. So that is so simple. and you could also write this property in the reverse sense, so that is quite obvious. And in another sense, when you have this convolution operator in on this frequency domain side, so what is the result? The result, it says that Fourier inverse transform of this f star g of omega, this is 2 pi into f of t into g of t. So this is the result, and you could also use this result in the reverse sense like this. So you should remember all these results in order to solve these Fourier transform problems, right? Next we have the Fourier transform of unit step function. Now what is unit step function and how do we solve this and how do we reach at this formula, we'll see in the later videos. Until now you should know what is this formula. This is the formula, 1 by iota omega. And Fourier transform of Dirac delta function, it is equal to 1. So these are few of the properties that we have discussed. In detail we'll see all of these properties in the course ahead. So I hope you got an idea of what we are trying to do here. So well, that is it for this video. Thank you for watching.